When we talk about topic models, you probably remember that first I told you about the distribution of topics in documents and distribution of words in topics. And then I said, but actually all this has to be estimated. And then we quickly discussed the ways of estimating those distributions. And I said that that goes beyond IR, and it does. But just the same way as in topic models here, all those examination and attractiveness probabilities, they are not given, they are not observed, they have to be estimated from clicks. So it is important to at least touch on estimation of click models so that you just understand what's the process and, well, what parameter estimation techniques we have in statistics. Well, mainly two, the maximum likelihood estimation and expectation maximization. So the first one, MLE, is used when there are no dependencies between parameters. So for example, in the cascade model, there's only one parameter, well, one type of parameter. There are many, alphas are many, but it's one type. Parameter alpha, attractiveness that depends on a query and a document. And those don't depend on anything. So those you can actually compute with MLE in linear time, essentially. So that is easy, but also cascade model and all those models that can be estimated using maximum likelihood estimation are usually not as expressive as more complex models where there is a dependency between parameters. So basically in expectation maximization, you can't estimate attractiveness and examination in position-based model, I'm sorry, in PBM, examination and attractiveness can't be estimated separately. They have to be estimated at the same time. And there we use expectation maximization, and we've already seen that for topic models, that the process is like this. We set parameters to some initial values. So we set all the examinations to something. For some reason, we use 0.2. You can use 0.5, but that's too aggressive. Then you set all the attractiveness to some value. And then you repeat E step and M step until convergence. So you derive the likelihood function, the expectation of the likelihood function, and then you maximize that expectation. And we did a lot of work in our book to derive the general formulas that could be applied to all the existing click models, at least click models that are based on probabilistic graphical models. That took probably the longest for us to write that chapter. And in the end, we came up with this set of simple rules that if you follow from top to bottom and you apply to every click model, then you get your estimation of the parameters. Now, let's try and see what works for PBM, for position-based model. As you remember, we observe a click, and the click depends on examination and attractiveness. And these two have to be estimated because these are exactly the parameters that we need, because alpha is, we believe it is relevance. So that's what we want to get out of the model. So we want to remove examination and we want to get a pure attractiveness. Now, how do we estimate these two parameters? Because you see they're both unknown and they both depend on click. And there exactly we use the lots of complex rules that I showed you on the previous slide. And we arrived to this, again, quite a scary equation at the first sight, but actually I'll walk you through and you'll see that it's not scary at all. And here what we do, we take alpha, EM is iterative, right? So alpha at iteration t plus 1 depends on alpha on iteration t. So, and importantly, it depends on both alpha and gamma. Otherwise, we would not need EM. So alpha depends on gamma and alpha, and gamma also depends on both of them. So alpha at iteration t plus 1 can be estimated from the parameter values at iteration t, these values. And actually, this equation is very simple. So let's see what's inside. Basically, we take a document, we take a query and a document, and what we need a query log, or click log as we call it also. So we track user clicks for some amount of time, and we collect all queries, all documents, and all clicks. And then we go over that log, click log, and we choose only pairs with a given query Q, with a given document D, because only those pairs will give us information on attractiveness. And that set is just, we call it as QD. So we go over all occurrences of a query and a document in our click log, and we check whether we had a click, this is click, on that document, or we didn't have a click. And if we had a click on that query document pair, we add that click to the estimation of attractiveness. Because it was clicked, then it means it was attractive, according to the model. If you remember, click happens if and only if a document is examined and attractive. So if click happens, that means for sure, according to the model, that the document was attractive. So if we have a lot of, so document and query occur many times. Because let's say, query University of Amsterdam, I observe the homepage of the University of Amsterdam, I click. You query the University of Amsterdam, and then maybe you don't click on the homepage, and then someone else clicks again. So we have many occurrences of the same query in the same document. Sometimes they're clicked, sometimes they're not. If they're clicked, this event here, then they are attractive. We should add to alpha. If they are not clicked, there can be two options. Either they are not attractive, so then we don't add anything because they are not attractive, so this parameter should not increase. And if, but they can be attractive, but maybe they're simply not examined. So they're good, but nobody actually read the snippet. And this is exactly the probability here. It is attractive according to iteration T, but it was not examined according to iteration T, and normalized by the total probability of no click. So you can see that this is easy. If we observe a click, we increase alpha. If we don't observe click, we increase alpha by alpha iteration T, but not examining at iteration T divided by the no click. And we do that for all the occurrences of the query and document in our click log. And that's it. I'm discussing this just to give you an idea what's going on when you do this kind of things. And this is the notation that I mentioned just for you. And this is the same for examination. We will not really go into detail, but you see that the formula is very similar. Again, if we observe a click, we add to examination. And if we don't observe a click, we add this fraction. So that's how estimation of parameters of click models is done.